Hello everyone, this is a video series on electromagnetic theory. In this video series, we will be starting with some prerequisites. Then we will discuss about electrostatics, magnetostatics, electrodynamics, and the final video will be on electromagnetic waves. This is going to be the first video of the series. In this video, we will discuss differential calculus, integral calculus, and we'll be discussing about spherical and cylindrical frame of reference. So let's start. In electromagnetic theory, you will come across different expressions like the surface integral of an electric field, or the divergence of an electric field, or the curl of a magnetic field. By the end of this video, you will be able to give the physical interpretations of these kind of equations. And also, sometimes when we try to solve a problem in Cartesian coordinate, the problem becomes very complex. Like, for example, if we have a solid charged sphere, and if you want to find out the electric field or electric potential at some point, if we try to solve this problem in Cartesian coordinate, it becomes very complex. But if we treat this problem in spherical coordinate system, the problem gets simplified. So the motivation of these videos is to have a basic understanding of the mathematics required to either give a physical interpretation or to make the problems simplified. We will be starting with differential calculus, and in differential calculus we'll be talking about gradient, and you can find the expression of gradient in the relation between electric field and electric potential, or in the expression of a force experienced by a dipole in a non-uniform electric field, and you can even find the expression of gradient in the gauge transformations. We'll be also discussing about divergence, and you can find the expression of divergence in Gauss's law, and by understanding the concept of divergence, you can even explain why there is no magnetic monopoles. You can even find it in the continuity equations. Then we'll be talking about curve. The expression of curl you can find in the relation between the vector potential and the magnetic field. You can find in Faraday's law and also in the Ampere's law. To understand gradient, let us take an example. Let's say we have a box, and let us assign a coordinate system to this box, and let us assume that the temperature depends on the x, y, and z coordinate of that particular point. Now, in this system, if suppose let's say we have a point A here, and this is the temperature. Let's say this one is x, y, and z. And suppose we make a small increment. By the way, the increment is assumed to be very small. So let's say dl is the small increment, and we are at the new point, let's say B. Now, the question is, when we go from A to B, what is the change in temperature? Now, the change in temperature will be depending on how x, y, and z are changing. So, we can write the change in temperature as the total derivative, which you study in calculus. So, the change in T due to the change in x, y, and z can be written as the partial derivative of t with respect to x dx plus the partial derivative of y, the partial derivative of t with respect to y dy plus the partial derivative of t with respect to z dz. Now, we can rearrange this expression in the form of a dot product. So, we can write x cap partial derivative of t with respect to x. Similarly, for the y term, we can write like this. Then for the z term, we can write like this. Okay, this should be z. Then we can take a dot product of x cap dx plus y cap dy plus z cap dz. Here, the second term, this term is the small displacement. Sometimes we call it infinitesimal displacement. And this term, the first term, we can write as a operator. This is the operator, and this operator is operating on temperature T. Now, this operator has a spatial name and a symbol. This operator, we call it the del operator, and this del operator is operating on T. Now, if I try to summarize, I can write this total derivative of temperature is equal to the dot product of the del T dot dl. Now we can write the change in temperature as del of T dot dl vector. Now this del of T is what we call as the gradient of T. Now if we recall the expression, gradient of T is equal to the del operator into T. So we can write this as like this: y cap partial derivative of T with respect to y plus z cap partial derivative of T with respect to z. So this is the expression of the gradient. Now this is a vector quantity. So whenever we take the gradient of a scalar function, we get a vector quantity. For example, if I have a scalar function f, and if I want to find out the gradient, then this will be equal to x cap partial derivative of f with respect to x plus y cap partial derivative of f with respect to y plus z cap partial derivative of f with respect to z. Now let us try to understand the physical meaning of a gradient. We will take the same example, that is dt is equal to the gradient of T dot the increment. Now we can write this dot product as the magnitude of the gradient of T. Since it is a vector, we can take the magnitude, and the magnitude of the increment into cos of theta. Here theta is the angle between the gradient of T and the displacement vector. Now if I fix the magnitude, if I take this quantity as a constant, and if I vary this theta, keeping the magnitude of the increment constant, and I'm varying the theta, and I will try to find theta where dt will be maximum. So dt will be maximum when cos theta is maximum. And when will be the cos theta maximum? When theta is equal to 0. So when theta is equal to 0, we can get dt to be maximum. But what is theta equal to 0? What is theta equal to 0 degree? Theta is equal to 0 means this vector is parallel to this vector. So using this information, we can say that the gradient of T is the direction where dt, that is change in temperature is maximum. So, what is the physical interpretation of the gradient of a scalar function? Gradient of a scalar function is the direction where the change of that particular function will be maximum. So, this is the physical interpretation of gradient. Now, we will discuss about divergence. The divergence of a vector is written as the dot product of the del operator and the vector. We already know the expression of the del operator, so we can write this, then the z component. Now, the vector v, I will write in terms of the component. So I can write vx, x cap, then the y component, then the z component. Now this vector v, it can be any vector. It can be electric field, it can be magnetic field, or it can be the velocity of a fluid. Now if we take the dot product, then we can get this expression, vx plus partial derivative of vy with respect to y plus partial derivative of vz with respect to z. So this is the mathematical expression of the divergence of a vector. Now, to understand the physical interpretation of divergence, let us take some examples from electrodynamics. Now, if we have a plus q point charge, the electric field lines would look like this. Now, okay, so I'll just write E here. If we consider a negative point charge, the electric field lines will look like this. Now, we'll take another example. Let's say we have a two metallic plates with equal and opposite charges, plus q and minus q. And if we neglect the electric fields at the boundaries, then the electric field lines will look like this. Now, for these three examples, if I want to calculate the divergence of the electric field, what will be the divergence of the electric field? Now, without doing the mathematics, we can get some idea of what will be the value of the divergence of E. In the first example, the electric field lines, they spreads out. In the second example, the electric field converges. And in the third example, the electric field lines are parallel. Now, the divergence of any vector, it tells us the information how this particular vector spreads out or converges with respect to a point. So if you see this example, the electric field lines are spreading out. So we can straight away write that the divergence of electric field for this case will be non-zero. Similarly, for the second example, it converges. So the divergence of electric field will be non-zero. But for the third example, it neither converges nor diverges. So in this case, the electric field divergence will be equal to 0. Now, by convention, whenever the electric field lines is spreading out, we take the divergence value to be positive, and if it converges, we take the divergence value to be negative. So in summary, divergence of a vector gives the information of how the vector field lines are spread out with respect to a particular point. Now let us discuss what is curl. Curl is defined for a vector, and curl of a vector is the cross product of del operator and the vector. Now this cross product we can write in a very compact form, in the form of a determinant of a 3 cross 3 matrix. So it will be a 3 cross 3 matrix. The first row will be the unit vectors. The second row will be the partial derivatives. And the third row will be the components of the vector v, px, py, and pz. Now let us try to understand what is the physical interpretation of a curl of a vector. To understand this, let us take two examples. One is, let's say there is a current carrying wire and the current flows in the upward direction. And if we want to find the magnetic field generated by the current flowing in that wire, we can use the right hand thumb rule, and the magnetic field will look something like this. In another example, let us take a point charge, a positive point charge, and we have drawn the electric field lines. Now, if we want to find out the curl of this magnetic field in this case and the curl of the electric field. Now, without doing the mathematics, we can get some idea of what the curl of these vectors will look like. Now, the curl of a vector, it measures of how much this vector v swirls around a particular point. This is the physical meaning of the curl of a vector. Now, using this definition, in this example, we can see that the magnetic field is circling around this wire. So, the magnetic field curl will not be equal to 0. But in the second example, the electric field lines are diverging out. So, it is not curling around any particular point. So, the curl of this electric field will be equal to 0. Now, let us discuss the spherical coordinate system. In a normal Cartesian coordinate system, we have x, y, and z direction. And if we take a point, let's say point P, this point P will be defined by x, y, and z. In spherical coordinate system, the same point will be defined by r, theta, and phi. So let us try to understand what is r, what is theta, and what is phi. Suppose if I assume that the origin of the Cartesian coordinate system as O, then this OP, this distance, this is what we call as the R. So, R is the distance of point P from O. Then what is theta? Now, from the z-axis, if I measure the angle to OP, that is this angle, this is theta. So here we can write down theta is angle down from z-axis to the line OP. What about phi? So for phi, what we'll do is we'll take the projection of OP on the xy plane. So this is the projection. I'll call this point as point P prime. Now we can join this. We can join O and P prime. Okay. So this OP prime is the projection of OP on xy plane. Now, the angle between the x-axis and the projection OP, this angle, this is phi. So, phi is the, let me use a different color. Phi is the angle from x-axis to OP prime, which is the projection of OP on the xy plane. Now, the R variable, R can range from 0 to infinity, and theta can range from 0 to pi, and phi can range from 0 to 2 pi. This is very important because when we use spherical coordinate system, and during the integration we need to identify the upper limit and the lower limit. We have learned that in spherical coordinate, any point P is defined by R, theta and phi. Now the next question is, like our Cartesian coordinate system, where we have three directions, the x direction, y direction, z direction, the spherical coordinate system have r direction, theta direction and phi direction. The answer is yes, we have three different directions, and they are denoted by r cap, theta cap and phi cap. Now let us try to visualize these three unit vector directions. So I'm calling this origin O. So from O, we will join this point P. The distance is R. Now, the direction of R cap will be along this direction, and it will be pointing outward. So I will write that as R cap. What about theta cap? So we know theta is the angle between the z axis and the OP. So this is theta. Now, if you see this theta from the z axis, it measures the angle. So the theta direction will be along this direction. So that one we can indicate it here. So this will be the direction of theta cap. What about phi cap? So for phi cap, we need to take the projection of this point P. Let's say this is P prime, and we can join this O and P prime, and this angle is phi. So like theta, phi is measured from x-axis to O. This should be P prime. Yes, this is P prime. So phi is measured from x-axis to OP prime. So the direction of phi will be in this direction. So that we can draw it here. It will be in this direction. Now, if you see carefully, this r cap, phi cap and theta cap, they are all mutually orthogonal. So since they are mutually orthogonal, we can write r cap dot will be equal to 1. R cap dot theta cap will be equal to 0. And r cap dot phi cap will be equal to 0. Now, let us try to find the relation between the spherical coordinate system and the Cartesian coordinate system. Now, if we have x, y, and z in Cartesian coordinate system, and we have r, theta, and phi, and let's say in both the coordinate system, we have the same point P. Now, how to convert from one form to another? Now, for this conversion, we can use the relation. Now, we can even do this by seeing this picture. See, this is point P. Now, if I try to take the projection of this OP on the z-axis, then whatever we get here, that will be equivalent to z in the Cartesian coordinate system. So we can write z is equal to r cos of theta. Now, what about y or x for that? Now, when I take this projection of OP on xy plane, we get this OP prime. And what is this OP prime? Maybe I can write it here. OP prime is equal to r sine of theta. Now, from this OP prime, if I try to take the projection of OP prime on the x-axis, it will be OP prime cos of phi. So, if I take this projection, this is what I'm talking about. If I take this projection, then this will be equal to OP prime cos of phi. And if I take this projection on the y-axis, then this will be equal to OP prime sine of phi. So using this relation, we can write x is equal to OP prime cos of phi, which is nothing but OP prime is r sine theta cos of phi. Similarly, y is equal to OP prime sine of phi, and this is r sine theta sine of phi. And this is the relation between the Cartesian coordinate system and the spherical coordinate system. Now we have already derived the relation between the Cartesian coordinate system and spherical coordinate system. So let me write down a relation here again. So x is equal to r sine theta cos of phi. Y is equal to r sine theta sine of phi, and z is equal to r cos of phi. Now, we can even derive the relation between x cap, y cap, and z cap, and r cap, theta cap, and phi cap. So I'm not going to do the derivation here. It's a bit lengthy, and if you are interested, you can refer to the book Introduction to Electrodynamics by Griffith. There the derivation is given. Here I'm just going to write the expression. So r cap is equal to sine theta cos of phi x cap plus sine theta sine phi y cap plus cos of theta z cap, and theta cap is equal to cos of theta cos of phi x cap plus cos of theta sine phi y cap plus, no, this it will minus of sine theta z cap, and finally the phi cap, it's equal to minus sine phi cap x cap, sorry, minus sine phi x cap plus cos of phi y cap. So this is a relation. Now I am writing this relation because I just wanted to point out something. In Cartesian coordinate system, x cap, y cap and z cap, they are independent. But in the case of spherical coordinate system, you can see from this relation that r cap depends on theta and phi, and theta cap also depends on theta and phi cap also depends on theta and phi. So as we change the value of theta and phi, the three unit vectors directions will also be changing. Now we will try to identify certain surfaces where one particular independent variable remains constant. So for that, let's start with the Cartesian coordinate system. So in the Cartesian coordinate system, we have x, y, and z. So if I want to have a surface where x is constant, then we can have a surface like this, which is parallel to yz plane, and it is intersecting at a particular point. So the value of x on the point on this surface will be constant. So here x is constant. Similarly, we can get a surface where y is constant, and that surface will be intersecting the y-axis at a particular point, and it will be parallel to the xz plane here. So here y will be constant. And to get a surface where z is constant, it will look something like this. It will be intersecting on the z-axis at a particular point, and it will be parallel to the xy plane. Here z is constant. Now the question is, can we have a similar kind of surfaces for spherical coordinate system? For spherical coordinate system, so we have r, theta and phi. Now let us try to find out what are the surfaces where r, theta and phi will be constant. Now if I take a Cartesian coordinate system, and if I draw a solid sphere with the center at the origin, then if you take any point on this surface, the distance from the origin will be constant, and it will be equal to the radius of the sphere. So this spherical surface, this is the surface where r will be constant. And for theta equals constant, we can draw a cone like this. And if I take any point on the curved surface of the cone, the angle theta will be the same. Theta will be the same. So this is for theta constant. And for phi, we can draw a surface like this. And if I take any point on this surface, the angle phi will be the same. So phi is equals constant here. Now this is very important because sometimes when we do for surface integral, we need to identify which is the variable which is constant and which are the variables which is changing. Now in Cartesian coordinate system, if I want to write the increment or infinitesimal displacement, I can write as dx x cap plus dy y cap plus dz z cap. So dx is the increment along x direction. Similarly, dy is the increment along y direction, and dz is increment along z direction. So we can visualize this. Suppose we have a point P here, and if I want to write the increment along x direction, it will be this, and this one will be dx. And the increment along y direction, let's say this is dy, and increment along z direction, this one will be dz. Now I can form a cube here by, I can form a cube like this. By the way, for demonstration purpose, I have drawn the figure big, but here we are considering it as a very small element. Now, if I want to find the volume of this, then d tau is equal to dx into dy into dz. Now, can we have a similar thing in spherical coordinate? Is it possible? Now, the answer is yes. So, let's take a point P here. So, this is R. So, if I want to change something along the R cap, then whatever increment we want to have, this is the dr, and this is along the R direction. What about the change in theta? So, let's say we have a theta here, and this angle, this is, let's say, d theta. Now, this portion is the change in the theta direction, because this direction is theta cap. So, what is this? This one we can write as r d theta. So, r d theta is the change along the theta direction. What about phi? So, for phi, we have to take the projection here. So, I'll take the projection here. Let's say this is the projection, and this is the angle phi. And let's say we are giving a small increment, say d phi. Now, the increment in the theta direction is given by this, because this is the theta, the increment in the phi direction. Let me just erase this. So the increment, this is the phi direction. So the increment along the phi direction is given by this. And what is this? Now, you can see that this quantity can be written as r sine theta. So if it is r sine theta, then this one will be r sine theta d of phi. Now, using this three information, we can write the small increment as, okay, along r cap it is dr, then along theta cap it is r d theta, and along phi cap it is r sine theta d phi. So this is the expression of the increment in spherical coordinate system. This formula is very important because using this formula, we can derive the divergence, gradient, and curl in spherical coordinate systems. Now let us write down the expression of the increment. That is dr along r direction and r d theta along the theta direction, and r sine theta d phi along the phi direction. Now using this, we can even calculate the volume element. The volume element will be the change along the r direction into the change along the theta direction and the change along the phi direction, that is sine theta d phi. So we get r square sine theta dr d theta d phi. Now, before concluding the spherical coordinate system, Let us do two exercise, and through this exercise you'll be able to appreciate that how powerful this coordinate system is. So this is a sphere, and we know the surface area of a sphere is 4 pi r square, where capital R is the radius of the sphere. Now for this problem, we are going to use spherical coordinate system. So in spherical coordinate system, we have three variables, r, theta, and phi. Now the integration is going to be a surface integral, that is two variables. So out of these three variables, one has to be constant and the other two has to vary. In this case, the small r is constant, because if you take any point on the surface, the small r is equal to the radius. So if I take a small surface area element ds, now ds will be the change along the theta direction, that is r d theta, and the change along the phi direction, that is r sine theta d phi. So this gives r square sine theta d phi. And we already know that small r is equal to capital R, so we can write as r square sine theta d phi. Now the total surface area will be equal to the integration of ds. So ds, it is a double integral. So we can substitute this r square sine theta d phi. Capital R square, we can take it outside since it is a constant. Then for sine theta d theta, the limit will be from 0 to pi. And for d phi, the limit will be from 0 to 2 pi. Now, if you solve this integration, you'll get r square, and here you'll get 2, and here you'll get 2 pi. So you get 4 pi r square. Now let us do one more example where we want to find out the area of a circle using spherical coordinate. Now we know that for spherical coordinates it is r, theta, and phi, and since we are going to calculate the surface area, one of the variable has to be constant. Now if you take any point, let's say point P here, for this point P, you'll always find that the angle theta is equal to pi by 2. But r and phi can change. So now we have identified which variables are going to change and which is constant. So if I take a surface area element here, so ds, so what will be this ds? This will be, we already know that r and phi are the variables which is going to change. So the change along r is given by dr, and the change along phi is given by r sine theta d phi. And here theta is equal to pi by 2, so we can write as r dr sine of pi by 2 d phi, and sine of pi by 2 is 1, so we get ds is equal to r dr d phi. Now the total surface of this circle will be equal to the integration of ds, and this is a double integral, so we have two integrals, one for r and one for phi. So r dr d phi. Now we can separate this d phi. What about the limit? For r, it will vary from 0 to capital R, that is the radius of the circle, and for phi it will vary from 0 to 2 pi. Now if we solve this integration, we'll get r square by 2 into 2 pi, so 2 cancels out, and we get pi r square, which is the area of the circle. Now let us discuss the cylindrical coordinate system. In cylindrical coordinate system, we have three variables: s, phi, and z. So to understand what is s, phi, and z, let us take one point P here, and the distance of point P from the z-axis, this is s. By the way, this is a perpendicular line. And this coordinate, this is what we refer to as a z. So the z in cylindrical coordinate system is same with the z in Cartesian coordinate system. And what about phi? For phi, we will take the projection on the xy plane. Let's call this one as P prime. And let's call the origin as O. Now this angle is what we are referring to as the phi. Now we can have a relation of the cylindrical coordinate system and the Cartesian coordinate system, that is s, phi, and z. So what is s here? What is x here? Sorry. So x, this, if I take the projection of OP prime, then this is x, and this is equal to s of cos of phi. So we have x is equal to s cos of phi. Similarly, we can find the y coordinate. So this is y, and this is equal to s sine of phi. So y is equal to s sine of phi. What about the z? Z is the same. So this is the relation between the Cartesian coordinate system and spherical coordinate system. What about the ranges of s, phi, and z? S, it can go from 0 to infinity. Phi, it can go from 0 to 2 pi. And z, it can go from minus infinity to plus infinity. Now, let us try to visualize the unit vectors of cylindrical coordinate system. So, for s vector, s cap, it will be in this direction. This is the s cap. And z cap will be the same as the Cartesian coordinate system. And the phi cap, the way how we have done in the spherical coordinate system, so phi will be in this direction. This is phi cap. So this s cap, phi cap, and z cap, they are mutually orthogonal. Now, we also have a relation of the unit vectors of cylindrical coordinate system in terms of the Cartesian coordinate system. So you can see the derivation in standard books, and for now I'm just writing the relation here. So s cap is equal to cos phi x cap plus sin phi y cap. Then phi cap is equal to minus sin phi y cap plus cos of phi y cap, and z cap will be the same. So this is the relation of the unit vectors of cylindrical coordinate systems in terms of the unit vectors of Cartesian coordinate system. Now let us try to visualize the different types of surface where r is constant, or phi is constant, or z is constant. So in the Cartesian coordinate system, if we draw a cylinder, then on this curved surface of the cylinder, you'll find that if you take any point on the curved surface of the cylinder, you'll find that its distance from the z is constant. And so this is the surface where S is constant. Now for phi, if you take this surface and if you take any point on this surface, you'll always find that the angle phi is constant. So this is for phi equals constant. And for the z, this is the same with the Cartesian coordinate system. So this is intersecting at the z axis and this is parallel to the xy plane. So here z is constant. Now, like the way we have done in spherical coordinate system, let us try to visualize the three unit vectors and let us try to find out the expression of the increment, small increment. So let us consider point P here, and this distance is S. So if I want to change S, then the increment, this increment along the S cap direction will be ds S cap. Now for the z direction, it will be in this direction and the increment will be dz in the z direction. What about phi? Now the direction of phi cap is similar to the spherical coordinate system. That is, if I take a projection here, okay, I'll call this one as P prime and I'll join this. So this is O, this angle is phi. Now if I take a small change in phi, say this is d phi, now this is the increment in the phi direction. So this OP prime, here OP prime is equal to S. So this increment in the phi direction will be equal to S d phi, and this is along the phi cap direction. So using this information, we can write the increment vector. So in the S cap direction, the change is ds. Then in the phi direction, the change is S ds, sorry, d phi. It is d phi. And along the z direction, it is dz. So this expression is the increment vector or infinitesimal displacement in the cylindrical coordinate system. Now we can write the volume element. This is increment along S direction, then into increment along the phi direction and increment along the z direction. So d tau is equal to S ds d phi and into dz. Now let us try to solve some numericals and appreciate that the use of cylindrical coordinate system simplifies the calculation. Suppose we want to find the volume of this cylinder, and we already know that the volume of a cylinder is equal to pi r square h, where capital R is the radius and h is the height. Now suppose if I want to use cylindrical coordinate system, so what I can do is I can take a small volume element here inside, say d tau. So d tau is equal to S ds d phi and d phi into dz. So the total volume will be given by the volume integral of d tau, which is a triple integral. So if I substitute this, so this will have three integral, one for S, one for phi, and one for z. So we have S ds d phi into dz. Now we can separate this. So for S, the limit will be from 0 to r. and for d phi the limit will be from 0 to 2 pi, and for dz it will be from 0 to h. So if we do this integration, we'll get r squared by 2, and for the phi integration we'll get 2 pi, and for the jet integration we'll get h. So this cancels out and we get pi r square h, which is the volume of the cylinder. Now let us try to calculate the area of a circle using a cylindrical coordinate system. So in cylindrical coordinate system we have s, phi and z, but we are going to calculate an area. So one of them has to be constant and other two has to vary. If you see the circle, it is in the xy plane. Since it is in the xy plane, z will be equal to 0. So z is constant and the variables which is changing are s and phi. Now let us take a small area element here. I'll call it dA. So this dA will be equal to the change along s, that is ds, and the change along phi, that is s d phi. So we get s ds d phi. So this is the area element. So the total area will be given by the surface integral of dA, which is equal to s ds d phi. Now we can separate this. For s it will vary from 0 to r, and for phi it will vary from 0 to 2 pi. So if we integrate this, we'll get r squared by 2, and for phi integration we'll get 2 pi. So 2 cancels out and we get the pi r square, which is nothing but the area of the circle. Now let us discuss integral calculus, and here we are going to focus on the portion of integral calculus which are going to be useful when we study electromagnetic theory. Now when we do integration, sometimes in the argument it might contain a gradient of a scalar function or the divergence of a vector function or the curl of a vector function. In such scenario, there are some fundamental theorems which is very helpful, and it can simplify the problem. When there is a presence of a gradient of a scalar function, we have the fundamental theorem for gradient, and when there is divergence, we have fundamental theorem for divergence. Sometimes this fundamental theorem for divergence, we have different names for this theorem. So one name is the divergence theorem, and it is also known as Gauss's theorem. And whenever there is a curl in the integration, we have fundamental theorem for curl, and this also has another name. It's called Stokes theorem. Now these three theorems have a very interesting property, and before we discuss in details, I would like to mention the property here. Let's say we have 2 points A and B, and we want to perform the integration of the gradient of a scalar function along a particular path. Let's say, suppose this is the path. And in another example, I have let's say a sphere, solid sphere, and I want to perform integration of the divergence of a vector function with respect to the volume. And in the third case, let us take a two-dimensional figure here, and I want to perform the integration of curl of the vector with respect to the surface. So this is the surface. Now, from the fundamental theorem, let's consider the first case. That is the line integral of the gradient of t, and it says that this is equal to the value of the function at the endpoint, the difference in value of the function at the endpoints. Now, if you see carefully, the line integral of the gradient is done in this path, but the final outcome depends only on the boundary of this path, that is at point B and point A. For the second example, the answer is the surface integral of the vector about the surface enclosing the volume. Now here also, the volume integral is performed for the divergence of A, and this volume integral is performed inside this volume, but the outcome depends on the surface integral, that is at the boundary. And for the third case, the answer is the line integral of the vector along the boundary. So by the way, this is a closed surface, and this is closed path. In the third example also, the surface integral, one vector symbol should be there. In the third example, the surface integral is performed for the curl of A inside here, but the outcome depends on the boundary. So you can see in all the three examples that the integration is performed inside the domain, but the outcome depends only at the boundary. So this is a common factor in all the three fundamental theorems. Now let us discuss the fundamental theorem of gradient. But before coming to fundamental theorem of gradient, let us recall some of your school physics integration concept. So suppose if I want to integrate f with respect to x from interval a to b, then this one will be equal to t a to b, where t is a function of x, and this one will be equal to tb minus ta, where integration of f dx is equal to t, which is a function of x. Now, if the integration of f gives t, then the differentiation of t will give f. So, if I substitute this in the first expression, then I can write the integration of the derivative of t with respect to x will give t of b minus t of a. Now, here we are dealing for a function of a single variable. Now, let us try to write in terms of vectors. And let's say t is a function of x. So if I want to find out the gradient of t, then it will be x cap, the partial derivative of t with respect to x. And my dl element will be x cap dot dx. Now let us try to evaluate this integration. Integration from a to b, the gradient of t dot dl vector. So if we substitute, we have ab, the two limits. Then the gradient of t is given by x cap del t by del x dot x cap dx. So since both are x component, the dot x cap will be 1. So this gives AB del t by del x dx. Now if we compare this with this, both are same. So the answer will be the value of t at B minus the value of t at A. So that means the integration of A to B, here we are working for one dimension. So if I try to generalize this to 3 dimension, then we can easily write the gradient, the integration of the gradient of t along a path is equal to the end values, the boundary values. So this is the mathematical expression of the fundamental theorem of gradient. Now we have got the mathematical expression, that is the integral from A to B for the gradient of a scalar function is equal to the function value at the 2 endpoints. Okay, A. So what is the meaning of this? Now to understand this meaning, let us take one example. Suppose you have a staircase, let's say, with different steps, and you are standing here and you want to measure the height. So this height will be a function of x. Now what you can do is, in order to measure the height, you can measure the height of each step and you can proceed till the top of the staircase. Then for each step, say, let's say hi, you can sum up this one, and if you sum up, then you'll get the total height. This is a discrete case, that's why I have used summation. If it is a continuous case, then it gives the integration. So, or there is alternative, there is an alternative way of doing it. You stand here, measure the height at the end point, and you directly go to the top of the staircase and you measure the height of the top point. Then if you take the difference, h of top minus h of the end point, then this also gives the total height. Now both the calculation gives the same result. Now the approach done here, this is analogous to the integration done here, and the approach done here, this is analogous to the right side of this equation. So both of them will give the same results. Now before concluding this, I would like to mention two special cases here. One is the integration from A to B of the gradient of this t. This integration will depend only on the 2 endpoints, and it will be independent of the path. Second point is, suppose it is a closed path, then this integration will be equal to 0, because since it is a closed path, the initial point and the final point are the same. So TB will be equal to TA. So the difference will be equal to 0. Now let us discuss the fundamental theorem of divergence. The mathematical expression is written like this. The volume integral of the divergence about a closed volume is equal to the surface integral of that vector around the surface and closing the volume. Now, to have a better understanding, let us replace the A vector by the electric field. So the expression will look like volume integral of the divergence of the electric field around about the volume is equal to the surface integral of E dot dA vector. And let us take this system. Here we have a point charge plus Q, and the electric field lines are coming out of this point charge, and we have a surface enclosing some volume V. Now, what is the divergence of electric field? We have already learned in the beginning of this video that divergence of E measures the spread of the electric field. Now, if I multiply this with a volume element, so what is the meaning of this? It's the spread of the electric field in that particular volume element. And here, if I do the integration throughout the volume, then this represents the divergence across the volume. So this represents the divergence across the volume. One more thing I want to point out here, that whatever the electric field coming out of the charged particle which are contributing to this divergence term, they are also passing through the surface because there are no negative charge. So whatever the field lines which are coming up from this plus Q, they are contributing to the divergence as well as they are passing through the surface. Now let us come back to the term on the right hand side. So for this, let us take a small area element here. So we call it dA vector, and the direction of this area vector is perpendicular and in the outward direction. Now, some of the electric field lines will be passing through this area element, and they are parallel to each other. So, what is the meaning of this? E vector dot dA vector. So, this expression represents the electric flux, that is, number of field lines passing through the area element. Now, if I integrate this, about the surface, then I will get the total field lines passing through the surface S. Now, here we concluded that the electric field lines which is contributing to the divergence passes through the outer surface. And here we are calculating the number of field lines passing through the surface. So both the integration carries the same information. So that is why these two expressions are equivalent. And that is what the fundamental theorem of divergence is. Now let us discuss the fundamental theorem of curl. I'm writing down the mathematical expression here. So the surface integral of curl of a vector is equal to the line integral of the vector along the path enclosing the surface. Now to understand this, let us take an example here. We have a two-dimensional surface and let's try to break down the mathematical expression. Okay, first we have this curl of a vector. So what is the meaning of curl of a vector? In the beginning of the video, we have learned what is curl. So curl of vector A, it is trying to measure the circulation nature with respect to a circulation nature of the A vector with respect to a particular reference point. Now, if I consider a small area element here, dA vector, whose direction is perpendicular to the plane, then if I take a dot product here, this is trying to measure the circulation of A in this area element dA. Now, if I integrate this throughout the surface, it is trying to measure the circulation of this vector A in the surface S. Now, let us assume that in each and every element, surface area element, the vector is circulating in a counterclockwise direction. Now, I am showing you the picture here. Now, the domain is divided into small area elements. Now, let us consider an area element inside the, means at the middle of the bound, at the middle of the surface. Suppose this is the area element. Now the vectors will be, the vector A will be circulating in a counterclockwise direction. Now this area element is surrounded by 4 other area elements like this. I'll call them as 1, 2, 3 and 4. Now let us draw the circulation of the vector A. So in 1 it is circulating in counterclockwise direction like this. In 2 it is circulating in counterclockwise direction like this. In 3 it is circulating in a counterclockwise direction like this. Similarly in 4 it is circulating in a counterclockwise direction. Now if you see carefully, here the direction of circulation, they are opposite. The red one is pointing towards the right direction and the blue one is pointing towards the left direction. Similarly here, and here. So the net effect will be 0. What about the area element on the boundary? So let's say this is at the boundary. So for this, the circulation will be in counterclockwise direction, and these are the 3 neighbors. So let's call 1, 2 and 3. Now let us draw the circulation. It's in counterclockwise direction. For 3 also it is in the counterclockwise direction. For 2 it's in the counterclockwise direction. Now here you can see that the inner portion of the path here and here, it gets cancelled. It cancels out, but the one at the boundary remains. And if you see here, for 2, if I draw the boundary, the nearby area element here, for 2 also, the inner one will get cancelled out, but the one at the boundary will remain. So the net circulation of this vector will be along this direction. So what can we say from here? When I'm dividing the surface into small area elements, the circulation of the A vector for the area elements which are inside will get cancelled out, but the one on the boundaries will remain. So the net circulation will be like this, or only the boundary terms will remain, or only the boundary terms will survive. So what is this? This is nothing but the integral of the A vector along the boundary lines along the part which is enclosing the surface. So these two expressions carries the same information, and that is what the fundamental theorem of curl is about. Thank you for watching the videos till then.